invitation to be here. When I was talking to my wife last night and describing to her the highly, in my experience, unusual hour for this talk, and I told her that it was an ironclad guarantee that there would be no undergraduates in the audience. And I also arrived here quite early today because I forgot that for the rest of the world this is actually a holiday, so there was absolutely nobody on the roads. And so, of course, the first person I meet in the lobby this morning was an undergraduate waiting for this talk to start. So it's making me rethink things, and perhaps maybe it's just Penn undergraduates who are lazy. Anyway, I want to tell you about an unusual line of research that I started a couple of years ago. I actually spoke on this very topic more or less just a couple of months ago in this very auditorium to a probably disjoint audience. It was for a DIMAX workshop on the intersection of computer science and economics. But from that experience and other experiences giving this talk, I find that it's easier to just start off by confessing to you exactly what it is we're doing and then back into the motivation separately. So this is a very literal slide describing to you the framework in which these experiments take place. So we've been running human subject experiments that I view, as you'll see, very deliberately at the intersection of topics in computer science, economics, and the term that I always put scare quotes around because it's a relatively new term, which is network science. So we bring in basically about 36 human subjects simultaneously into a laboratory, and everybody sits at a workstation which is interacting with a server system that we've developed down at Penn. And each subject is controlling some simple property of a single vertex in some underlying network that we have exogenously imposed on the participants. And subjects have only local views of the activity, so they basically see the state of their own vertex themselves, if you like, and some information about the state of their neighboring vertices. And I'll be a little bit more precise by what I mean by a local view shortly. And subjects have a real financial incentive to solve their piece of a collective global problem. So in particular, we're paying subjects real money for participation in these experiments, and adopting the principles of behavioral economics, we're paying them not for participation, but for their actual performance in the experiment. So there's a measure of quality of their performance, and we're paying them accordingly. So let me be precise. Here's a simple example that we'll discuss at some length, which is the problem of graph coloring. So in the graph coloring problem, you sit there and you can asynchronously update the color of your vertex from some fixed menu of colors that we're giving to the participants. You basically see your color change when you decide to change your color, and you see the colors of your immediate neighbors in the network change as they decide to change their colors. And basically, you get paid some amount if at the end of that particular experiment, your color differs from that of all of your neighbors. Otherwise, you get paid nothing for that particular experiment. And we run a lengthy sequence of these experiments in a single sitting with the same set of subjects. So you can see here, we basically designed a little behavioral game, a little distributed game theory exercise in which the so-called max welfare solutions, i.e. the configuration of the global state which causes the experiments to cost me the most money, actually corresponds with some interesting combinatorial object, in this case an optimal coloring of the underlying network. Okay? And so this is the basic framework we're working in. We've done several sessions of these over the past couple of years. The sessions themselves are extremely time-consuming to design, to execute, and then afterwards you have this very, very rich data, and it takes months and months of deciding what analyses to do in the data. But basically across many experimental sessions, we've deliberately varied at least two main design variables. One is the network structure itself. What does the topology of the network or graph look like? And what is the actual problem or game they're playing? In this case, it's graph coloring, but as you'll see, we've tried several different problems as well. And you'll generally see that the networks we've chosen are inspired by some mixture of models from the so-called burgeoning field of network science, much of which has played out in the literature, the pages of Science and Nature, alarmingly. But if you're familiar with terms like small worlds models or preferential attachment, you'll see we're taking networks from those probabilistic families, and also some ones that we carefully handcraft because we think they might lead to interesting or enlightening behavior by the participants. And the problems we've chosen are basically chosen for their diversity along a couple of dimensions. One is whether it's a cooperative or a competitive game, so I think of coloring as a cooperative game because it is possible for everybody to simultaneously be paid. Other games you'll see don't have that property. And also, as somebody with a theoretical computer science background, I'm also interested in how the behavioral difficulty of these different problems relates to what we know about the centralized computational difficulty of these problems from the viewpoint of, let's say, computational complexity. Okay, so this is the background and overview. Now let me tell you a little bit about what some of my motivations are in initiating this line of work. So one of the most interesting questions that really started, for me at least, with theoretical interest. So I've been spending many years, as some of you may know, looking at network models of game theory and economic systems, market exchange models, so on and so forth. And part of that research line is algorithmic, which I really won't talk much about today. But part of it just asks interesting questions, such as if you have a game or economic system taking place on some kind of network structure, how does the topology of that network influence the actual economic outcome? So for instance, if you have some sort of economic exchange taking place on a network, what does the network structure tell you about the wealth that everybody would enjoy at theoretical equilibrium in such a model? Okay, and so this naturally led to my being interested in the same question in actual behavioral settings, i.e. if you really have people play these games, how does that relate to the network structure, and how does it relate to what the equilibrium theory says about the network structure? As a side comment, I would point on that you know, there are many communities now that are littered with many papers documenting that certain types of structural properties seem to arise again and again in naturally occurring networks, whether they be social networks, economic networks, organizational networks, sometimes biological networks. So for those of you that are familiar with popular writings of things like Malcolm Gladwell's The Tipping Point, you know, there's this great discussion of hubs and connectors and this implication that they play some extraordinarily important and usually very positive role in problem solving, navigation within social networks, so on and so forth. And so there are many theories or suggestions of this kind, but if you think about it, there is almost no actual experimental corroboration of some of these theories and models. And in particular, there are field studies where people go out and say, oh, well, look, if you look at the exchange of email between members of the Rutgers computer science department, lo and behold, look, here are the connectors of that department. And there's this implication that if they weren't there, something would break, right? Or that some other connector would have to come to life. But you can't really, even from empirical studies of that kind, you can't do counterfactual testing, right? You can't know how the network might have behaved or worked or not worked if those people hadn't been there. To do that, you really have to do some kind of controlled experiments, okay? And I'm not claiming that these controlled experiments will answer that question, but I am advocating controlled experiments to answer that kind of question, okay? So another, problem or question that we're definitely after is not just how does network structure influence individual and collective behavior in these experiments, but how does this influence depend on the problem being solved and how? So again, is it always a good thing to have hubs and connectors with extraordinarily high degree? Is it always a positive thing to have a network with small diameter, so on and so forth? As I mentioned, I'm also definitely interested in the question of how the behavioral difficulty of different problems relates to traditional computer science theory. Just for the aficionados or zealots, as you might call them in the audience if there are any, no, I'm not proposing collective computation as a challenge to the Church-Turing thesis or any of the kind. But I do think it's interesting to ask whether complexity theory and its variants has anything to say about what distributed populations of human beings interacting with each other only from local information has to say about such models or such settings. I'm definitely interested in what kinds of heuristics people actually adopt in trying to play these games and whether human behavior exhibits either familiar or interesting algorithmic properties. And more generally, I'm interested in just what kinds of problems do people seem to be able to solve, and how does it compare to various equilibrium theories that we have from game theory and economics on these problems, okay? And so I hope by the end of the talk you'll see that what I'm after here is a set of questions that I think are of general interest and the source of a great deal of activity in several distinct but as time goes on, I think more and more unified communities, namely the group of people in economics that are interested in network settings, the growing field of algorithmic game theory, which is largely played out in computer science departments, the whole literature on social networks and the like. Okay, so let me just quickly give you an overview of the different experiments we've done to date, and then I will spend a little bit of time talking briefly about some of the simpler ones, and then I hope to spend most of my time on the final one. So the earliest experiments we did were back in January of 2006, and we did kind of revisitation of these experiments in February 2007. Were, as I described before, these graph coloring experiments. So I'm going to quickly tell you a few things about each one of these experimental sessions. In the graph coloring sessions, the player basically controls the color of the vertex. The number of choices for the color given to the participants was exactly the chromatic number of the graph. So we're trying to force people to find optimal colorings of the graph. It would have been perfectly reasonable to allow some approximation and give them twice as many colors or one more color than is necessary. We decided to go for it. One of the things that's interesting about doing these experiments is that since they're basically unprecedented, right? I can't go out and look in some literature to answer, well, do I think that 36 people in a couple of minutes could successfully, a three-colorable graph drawn according to preferential attachment? I had no idea. And pretty much for every one of these experiments, I have no idea. And this is a problem because these experiments aren't just potentially expensive, they're very, very time-consuming to set up and design. And so your biggest fear as a researcher in designing these experiments is that one of two things happens. Is you basically, bring to the collective a set of problems and they just can't solve any of them. And then the other thing that, of course, is bad is the opposite, is you give them and everything's absolutely trivial to them. So you definitely, you're trying to design experiments that explore some range of difficulty and behavior in the participants. And so it's easy, if you don't think carefully ahead of time, to give them either trivial or too difficult exercises. But so we went ahead and decided to see if they could do optimal coloring, and as you'll see, they're actually quite good at it. The payoffs in these experiments were for each individual coloring experiment, again, of which there was a sequence of in a single session. An individual player got paid $2 if their color was different from all their neighbors at the conclusion of the experiment. Otherwise, that individual got $0. The max welfare states, if we think of this as a collective game, are the optimal colorings. And just to remind you, we know quite a bit about the difficulty of this problem from the perspective of centralized computation. It's one of the nastiest NP hard problems in the sense that even if you allow certain kinds of very, very poor approximations, it's still NP hard. Okay, and so this is one of the reasons we chose this problem to start with. The other thing that's nice about a lot of these problems, drawn from the Gary and Johnson tradition, is that even though their computational difficulty and the algorithmic complexity of them may be quite high, civilians can understand the point of these problems very quickly from very brief instructions. And something like coloring is also highly visual, right? You're sitting there, you see your color, you see neighboring colors. We give them an interface which highlights neighbors that they have a conflict with, so on and so forth. But people can quickly understand what the problem they're trying to solve is. Okay? Now, very similar to coloring, but in some sense the opposite, is consensus. Again, here the player controls just the choice of a color from some fixed set. Now the goal, though, is to be the same colors, for the collective to converge on a single color. So basically each individual gets paid if at the end of the experiment they're the same colors, all their neighbors otherwise 0. The max welfare states are obviously the ones in which there's only a single color across the entire network. From the viewpoint of centralized computation, nothing could be a more trivial problem. If you want to think more broadly, these are actually pretty natural, simplified cartoon models of two kinds of natural social problems. One is which you want to differentiate your behavior from your neighbors, and the other one is what you want to agree with your neighbors. So, if you want to think of natural examples where you want to solve the graph coloring problem, if you're going to a party, you don't want to be wearing the same thing as your friend. Again, somewhat in the tradition of only the lunatic fringe of computer science research being published in Science, we actually published these experiments in Science, and the editor really pushed on me to try to give a natural, everyday example of where people wanted to solve graph coloring. And she wasn't happy with, universities all the time when they need to schedule exams essentially have a coloring problem. And so the best example I thought of was cell phone ringtones. Where you basically want to have a different cell phone ringtone than the people you're frequently interacting with. It's reasonable to assume there's sort of a finite vocabulary of such colors. and you want to be different than your neighbors. Okay, so consensus is sort of the complement of graph coloring, and we did a session of consensus and coloring experiments together directly paired on the same underlying networks. I won't say much about it, but we also did one with independent sets. So an independent set, basically, you want the population to somehow identify a subset of themselves, which is a maximum independent set of the graph. There's, again, many design decisions about how to create an interesting game which will incent people to do that. But basically, the way we did it is everybody just declares themselves to be a pawn or a king. If you're just declaring yourself to be a king, you're essentially asserting that you're in the independent set. If you're declaring yourself to be a pawn, you're being passive and declaring yourself not to be in the independent set. The highest rate of pay in this game comes from being a king and having no kings next to you, which is the constraint of an independent set. If you're a king and there's a king next to you, then you get nothing during the period that both of you are kings. And if you choose to be a pawn, you can always get some intermediate rate of pay independent of what your neighbors are doing. Okay, and again, this is a problem where I've arranged a game in which the max welfare states are the max independent sets. And again, this is a problem that's particularly nasty from the viewpoint of centralized computation. Now, the way the structure of the talk is going to be, I'm going to give you a quick tour of sort of the interesting findings that happened here, just to kind of warm us up and let you think about these experiments. I generally find that people enjoy this talk because it causes them to think about their own alternative experiments and designs, which is always a fun thing to think about and to talk about. But so I just want to warm up with these experiments because they're especially easy to visualize what happened and just tell you about some of the findings here. And I hope to spend most of the talk on these experiments down here, which we ran just back in April, and we actually just finished finally writing up the first set of findings we have from the data. I'm going to defer a detailed explanation of this game until we actually get to it. But basically, it's a very simplified version of traditional exchange economic models that are common in mathematical microeconomics, in which players basically are incented to trade goods with each other. There's actually just two types of players, and they sit on opposite sides of a bipartite graph. And they each have incentive to engage in trade with the other side, but they can only trade with their neighbors. And the payoffs that they get in this game, the amount that I actually paid them in real dollars, is proportional to the amount of the other good they obtain. So you start off with milk, the other side has wheat, but if you're a milk player, you only get paid proportional to how much wheat you got in exchange for your milk at the end of the game. We don't value your initial endowment at all. The max welfare states here are well known to be the so-called market clearing equilibria, where the market clears in the sense that all the goods on one side end up on the other and vice versa, and everybody behaved rationally along the way, meaning that they got kind of the best prices that they could or the best exchange rates available to them in their local neighborhood. This is an interesting problem from the viewpoint of centralized computation in contrast to the sort of trivial to intractable range that we had up here. A very nice algorithm that uses linear programming as a subroutine was just discovered by about 4 or 5 years ago, which is actually the algorithm we used to compute the equilibrium vectors that we could then contrast with the behavior in these experiments. So this is nice in that it's sort of the boundary of, if you think of algorithms that use linear program as a subroutine as being at the boundary of efficient computation, then this problem sits at that boundary. Okay, so what I want to do now is describe the coloring and consensus experiments just in terms of quick highlights. To acknowledge my co-authors along the way, the initial set of coloring experiments that we published in Science was done with my then doctoral student Sid Suri and another Penn graduate student, Nick Montfort, and the second session that I'll kind of mix in was done in collaboration with Stephen Judd, who continues to be my partner in crime on more recent rounds of experiments. Okay, so this is a typical type of interface that a user would see in either the coloring or consensus experiments. The view of the partial view, the local view of that an individual has of the global network is what we call a first neighborhood view. In social network theory, it's sometimes common to call this first neighborhood view the ego network, because it's basically showing you just information about yourself and your neighbors in the network. So in this interface, right, so this is a coloring problem, so let me just take you through some elements of the interface. At the top, there's a simple gain progress bar, which just goes monotonically from left to right until the time limit for the experiment is over. You have to put time limits on these experiments, right? Because Otherwise, you might have planned to go through 25 coloring exercises, and the first one took, you ran it for 2 hours, and everybody's exhausted, and if they still haven't found the coloring, you just can't tolerate it. So there's a little progress bar. There's current payoff that tells them how much they would currently get if the game ended now. And then down here you have the panel which visualizes your very partial view of what's going on in the network. Here you have dark edges connecting you to your immediate neighbors, and then we're also showing you connections between your neighbors, okay? So of course there's some much larger network that this is just a piece of, but this is what your view of it would be. You can see that down here there's the action panel where you can just click on these buttons and change your color. It will asynchronously update your color to your view and the view of all of your neighbors, basically anybody who's allowed to see it. And similarly, if they change their color, you'll also be able to see it. The integer annotating each of your neighbors is telling you how many other neighbors they have besides you. Okay, so we're giving a little bit of non-local information, not just showing you yourself and your neighbors. We're also telling you, if you like, how busy your neighbors are, how many friends your neighbors have. So this particular case, right, which is just a sample view, you can see that this is telling you that you're in an isolated component with these three because they have no other neighbors. But in general, in the games, you might, you would generally see positive values for the number of neighbors that your neighbors has. Okay, but again, this is the number of neighbors other than yourself. So if you see a 6 here, it means that this guy has 6 neighbors other than you, 1 of which you can see and 5 of which you can't. Okay, and so this is just a crude measure. As a motivation or justification for this particular view, which by no means is the only one you could consider and is not the only one we experimented with, as I will describe in a second. I view this as the maximum amount of information that you could actually expect a human being to document about their own social network, for instance. Okay, so I believe that most of you, if I gave you the exercise, if I gave you some definition of friend or neighbor in a social network and asked you to write down the names of all of your close friends, I think you could mainly do it. I don't think you'd get them all, but I think you could get, maybe 95% of your close friends. If I asked you to tell me which of your close friends are close friends with each other, I think you could get a lot of those edges. I think if I asked you which of your friends is very popular and which are very unpopular, I think you could give some approximation to that. But I think if I asked you for any information outside of this picture, you'd be very, very hard pressed to document it. Like, for instance, writing down the names of the close friends of all of your close friends. So this is sort of viewed as maybe it's even gone a little too far, but I certainly think it's the maximum amount of information you could cognitively expect a real person to keep track of about, say, their own real social networks. Okay? So in the first set of coloring experiments, what I'm showing you here are samples from each of the different types of networks that we used. And so this kind of picture is very typical, and I'll show you a couple more pictures like this. And what I'm just trying to do here is give you a sense of both the arbitrariness with which we choose networks for these experiments, and I think that arbitrariness is basically necessary, right? And it's necessary, again, because these experiments are largely unprecedented. And so one could look very narrowly, sample very narrowly from one very, very limited set of networks or stochastic models for network formation, and then you'd learn quite a little, you might learn quite a bit about an extremely narrow part of the experimental design space. We see it somewhat as our moral duty as the first people wandering into this area to at least just try to populate, even if it's in a somewhat scattershot fashion, a much wider range of choices for this design variable. So in the first set of experiments, we basically chose networks from one of several families. So the 3 networks across the top are basically have been drawn stochastically from what's known as the small worlds family, on which there's a large literature by people ranging from John Kleinberg at Cornell to Duncan Watts at Columbia, who's a sociologist. But in these models, what you basically start with is some very regular underlying network structure, like a cycle, or if you want to do it in 2 dimensions, it could be a grid, or you could do it in a 3-dimensional cube. But the basic idea is you start off with all of the network, all the vertices connected by some very regular topology. which, again, if you've never seen this literature, the motivation might be hard to back out, but I'll quickly give it to you. The basic idea is that this very regular lattice-like structure is meant to model something like geography. So the idea that you meet people, one of the ways that you meet people in life is by physical proximity, and that physical proximity is being modeled by this highly regular sort of geographic structure where, you live out in farmland and you only know your neighbors to the left and right on some long country road. And then probabilistically, you have a knob which says, well, I'm also going to add to this underlying very regular structure some random connections which are meant to model other ways that you might have of meeting individuals that would cause this very, very limited geography to be grossly violated and give you connections with people all over the world. So this is the idea that sometimes you travel from your little country road and you take an international flight and you meet an interesting person on the plane next to you, and that causes these long distance connections. So in general, we played around with, so this is sort of one extreme of the model where there are no long distance connections, and then you can layer in more and more long distance connections, and usually this is done stochastically. And of course, if you sort of add enough long distance connections, then basically, intuitively, the original lattice structure becomes largely irrelevant, and the connectivity pattern becomes largely dominated by the long distance. So if you add in enough random long distance connections, you essentially are at a random graph model, something like an Erdős-Rényi model, because the influence of the original lattice structure is being basically eradicated by the random edges you're drawing. So among other things that happen as you add in these long distance edges is obviously the diameter of the network is going to decrease quickly, but other properties are going to change as well. So we chose networks of this kind, and by the way, the colorings on these networks are actual solutions found by the population, okay? And so you can see that we didn't quite add random chords in these models because you started with a two-colorable network, and each of these is still two-colorable. And the reason we did that is we wanted to add random chords in without increasing the chromatic number of the network, right? Because we wanted to only tune one knob at a time. So if you add more chords in general, you would expect to increase the chromatic number of the network, which also in some sense makes the problem easier. By basically just adopting the simple constraint that we only add in chords between differently colored vertices in the original cyclical structure, we basically create a situation in which as you add edges, from the local perspective of any individual in this network, the problem's only getting harder, because they still only have two colors to choose from. But now this guy has many, many more constraints to satisfy than he did in the original graph, okay? So this allows us to kind of add chords in a way that keeps the problem only more difficult for the individuals in the network, even though we're changing other structural properties of the network. By the way, quick methodological point. In every experiment within a session, we have 36 people in the room, and as we go through a sequence of experiments, no matter what the problem is, no matter what the network is, for every new network, we are randomly on the fly, the system is randomly reassigning individuals to a new vertex in the network, okay? So there's no real opportunity here. There's opportunity for learning about how to play the game in a global sense, but there's no learning at the level of like, oh, well, this person was uncooperative with me last round, so I'm going to be uncooperative with them this round. You basically are playing, your neighbors are a new random set of individuals with every new experiment, okay? So this is one family. We also, since we were looking at kind of cyclical structures, we also threw in this thing that we call the leader cycle. So in the leader cycle, you have, you sort of take two people out of this cycle. You still arrange the rest on an outer cycle, but then you have two very, very high degree vertices in the middle here that are connected to alternate vertices on the outside. It's still two colorable. Why did we throw this in? Well, it's thought-provoking thinking about whether this should be easier or harder than other things on the screen here. So one theory, of course, would be what needs to happen in this network is that obviously, as soon as the game starts or very quickly after it, by the way, everybody starts with no color at all, and to get paid, you actually have to enter the game and choose a color at some point. In this particular experiment, it's natural to hypothesize that very quickly after the experiment starts, each one of these vertices will immediately find that the two colors are already used in their neighborhood, and there's no choice they have but to conflict with one subset or the other of their neighbors. And so what should happen, so to speak, which is why we call it the leader cycle, is that these two should coordinate the different colors with each other. They're connected too. And then once they do that, they should just sit there, right? And the others should arrange their colors in a consistent fashion around those two. These last two networks, which look like true rat's nests, actually have a fair amount of probabilistic structure to them. They were both generated according to a well-known model called preferential attachment, which if you've never heard of it, I will very briefly summarize in English. In preferential attachment, you build the network incrementally, adding one vertex at a time. When you add a new vertex to the network, you add some number of edges from that vertex back to the existing network. The edges, the new edges from the new vertex back to the existing network are chosen randomly, but not uniformly. They're chosen according to the current degree distribution of the existing network, okay? So basically, this is sometimes called a rich get richer model, because if a vertex already has a high degree in the network so far, not only do they have a high degree so far, but they are preferentially more likely to get new incoming edges. So there's an amplification effect in terms of degree. So the very reason that this model was formed is that it's one simple distributed natural explanation for how networks get a heavy tail degree distribution. Okay, so in particular, the degree distributions that result in this process will be a power law form, okay, which if you read Science and Nature, you'll know arises ubiquitously in networks and other areas of science and nature. And so the only difference here is between the density of the two. And so many people think of preferential attachment as a reasonable approximation to how something like the web graph might grow. Right, so all the time, new web pages come online. They link back to, they add hyperlinks back to the existing network. Of course, those hyperlinks are added for a reason, no doubt. But if you blur your eyes, you could imagine, well, they're more likely to be added to pages that already have a lot of incoming links, just because one of the ways people find out about web pages is by surfing the web or using Google, which takes link structure into account. Okay? So just to kind of, whet your appetite for these experiments, let me show you a couple of home movies. These are sped up by a factor of 2 or so, I think. And this is showing you, sped up slightly, the actual behavior of participants trying to two-color a simple cycle from only local information, okay? And the orange edges, which should be harder to see, or at least the black should be highlighted, the black edges are where there are color conflicts, like these two adjacent red vertices down here, okay? And so, it's fun when designing these experiments to think about what should be easy and what should be hard for the human subjects. The one thing that's particularly nice about the cycle is there's a sort of almost an inevitability about what has to happen in the dynamics here. So in particular, if there are two conflicts, if there are two black edges somewhere on the cycle, the only way these edges can get resolved is by finding each other, by being propagated by the population towards each other so that the vertex in the middle can resolve the conflict. And in fact, much more enlightening than watching this even at this speed is if I grab this bar and sort of pull it back and forth, you can see this effort to propagate the, even though from only local information, there's some sort of clear purposeful effort. You can definitely see the black edges propagating. The problem is that with no global view, the people that are propagating this thing clockwise have no way of knowing that actually there's another thing, going clockwise also, and that one of them needs to reverse, okay? So this is actually an experiment where I think in this session they were given actually fully 5 minutes per coloring experiment. Once we realized people were better than we thought at this stuff, we cut the time down so we could do more experiments. But this is an experiment where after 5 minutes, there were still several conflicts remaining in the network at the end of 5 minutes. So they did not succeed at coloring this cycle in 5 minutes time, okay? In contrast, here's an example of a preferential attachment network, which in this case happened to be 4 colorable. Again, sped up slightly. And if you think about what needs to happen here, the dynamic is very different. So again, these very, very high degree vertices in the middle, like this one here, the layout is generally such that the layout that I'm showing you here, which again the participants are not seeing, this is kind of the control panel here, the mission control view that you're getting here. It's quite often the case that these high degree vertices in the middle will find themselves, immediately with all of the available colors used up by their neighbors. So the only choice they have, there's no solution for them. Their only choice is who do they impose, who do they choose to, be in conflict with, and then what needs to happen is that basically and this is a case where in a very short amount of time they actually did find a solution to this apparently much more complicated network. But what needs to happen is that conflicts need to propagate from individuals like this vertex 1 in the middle here, who has, I don't know, something like 18 or 19 neighbors. And they need to somehow be passed out to vertices like number 35 here, who is a degree 3 vertex in a 4 colorable graph, and therefore can resolve any conflict that arrives there. Okay? So food for thought. It can be fascinating and a huge burn of time to stare at these videos. Now, I also mentioned that we in a second session of coloring experiments, we also paired it with consensus experiments, okay? And when we paired it with consensus experiments, we looked at a different set of network architectures. And what I'm showing you here is, so one of the things I'm hoping is if at some point this line of research doesn't work out from an academic standpoint, I'll have an alternate career in postmodern art. So let me describe what these are showing you here. So over here I'm showing you a network structure over 36 vertices, which is a chain of 6 cliques, each of size 6. Okay? So again, this is a very common kind of toy model to look at in the network science literature. You start off with something which is very tribal, if you like. You've got these 6 little clans, each of which has maximal interconnectivity. Each of these is a 6 clique. And then each clan or tribe, if you like, has a leader that's in very, very loose communication with some leader vertex of the 2 adjacent clans. Okay? So you can start with this kind of network, and then of course you can move from this to something much more highly connected by a variety of means, either by adding random edges in, or in the case that we did here was we had a parameter p, which is a probability, and you go to every one of the clique edges, and with probability p, you rewire it to a random destination in the network, and with probability 1 minus p, you leave it where it is. So if p is equal to 0, you don't do any random rewiring, and this is the network you get. If p is basically equal to 1, so you're going around and random rewiring all these edges, you get a network that's of the same edge density, but is essentially like an Erdős-Rényi random graph. Okay? So again, you have a single knob which lets you move between a highly sort of tribal culture, if you like, to one where there's no structure. Every pair of vertices is equally likely to be connected as every other pair. Okay? So what I'm showing you here are visualizations of the actual behavior that I personally find fascinating for small values of p. Either p is equal to 0 or maybe p is 5 or 10%. So you're still largely preserving this underlying clan structure that you see here. And what each one of these little visualizations is showing is for a different experiment. Time is running on the x-axis here. And on the y-axis, you have a colored bar for every player in the game. And I'm simply showing you with these bars what color everybody's playing as a function of time. And of course, I've arranged it here so that, this 6 clique is the first 6 rows. The next 6 clique is the next 6 rows. So there's visual proximity between players that are in the same clique in this network. Okay? So first of all, you can see some, expected and unexpected and fascinating behaviors here, both at the collective level and the individual level. So in general, you see that in each one of the experiments, you quickly converge to a small number of colors, right? And it generally tends to be in blocks. So here, this clique started off trying to be brown. They were adjacent to the next 2 cliques in the chain had already converged to yellow. So at some point, there was enough communication to actually convince this clique to drop brown, and then this entire half of the population more or less remains yellow throughout. On the other side of the network, so to speak, say up here, there's a fair amount of disagreement, so at about the midway point through the 2 minutes, basically the population, there's a standoff, right, between these 2 colors, okay? That in this particular case eventually gets resolved. Now, meanwhile, you see all kinds of very interesting acts of individual behavior. So you have, for instance, what I would call signaling behavior here, all right? So, you give people this limited interface to communicate with, but they will try to use it to communicate in meaningful ways. So here is probably somebody in a brown network which has a neighbor up here who's experimenting around periodically trying to get his brown neighbors in this clique to, agree with this yellow group up here, okay? You see people with various kinds of random experiments. You see, who is this cowboy here? one choosing this color. My favorite one is this one down here in the lower right. This is the only one of 18 consensus experiments on this night in which it did not finish with a solution, okay? And so what happens here is you very quickly get to 2 or 3 colors. This, of course the colors I'm showing you here are just arbitrary artifacts of the plotting, but you have this sort of light green here, this darker blue here, and orange, and pretty quickly those are the only 3 colors remaining. This clique up here remains this color for quite a while, but at some point gives it up and switches over to the dark blue, which right about here is the vast majority of the population. Right before they switch over to dark blue, though, they manage to have a trickle effect into the neighboring clique of this light green color, which then goes on, in fact, to sweep this entire other half of the population, and you can see this back and forth. So there's a switch from what's going on here to, say, at this point, when now the majority up here is blue and there's a small green down at the bottom. Okay, and you can see that it ends with about half of the population is dark blue and half of the population this light green. Okay, so all right, so I've shown you lots of pretty interesting pictures. One of the things that's surprising to me about this research, especially as somebody with a machine learning background and active machine learning interests, is I kind of went into these experiments thinking, well, we have 36 people, and we're running 20 to 30 experiments in a given night. I sort of went into the work more or less convinced that I would never be able to report other than average or mean values and never make statements about statistical significance. And I've been pleasantly surprised in that at least all of the top level findings that we've generally wanted to make, almost all of them we've been able to report with strong statistical significance backing them up. And so I won't regale you with that along the way, but in general, any statistical statement I make about the results in these experiments or other ones, unless I note otherwise, is statistically significant under the appropriate test, whether it's a t-test or some other kind of test, at the 5% level, or in many cases much, much lower. So what are the kinds of more scientific things that you can claim? So first of all, there's generally strong collective performance. So we gave people these time limits from 5 minutes in the very first session for coloring down to 2 minutes for either coloring or consensus in the second session. And generally the collective performance is quite strong. People can indeed color using the maximum number of colors, a wide variety of network structures in just a couple of minutes. And by the way, just to give you a back of the envelope sense, obviously if I gave any of you a 2-cycle to color, and I also, by the way, laid it out for you as a 2-cycle so that you could clearly see that it had that structure as opposed to drawing it in some arbitrary rat's nest way, you could definitely do it. But most of the graphs we're giving to people, if I gave you pencil and paper and asked you to color this, like a preferential attachment for a colorable graph, I believe that most of you would struggle to color those graphs properly, within a working day. Right? So they're complicated things, and if you start trying to do it by hand, you'll very quickly find yourself stuck. So when you give these things, though, to a distributed population and only give them local views, it seems that they can do them rather quickly across a pretty wide variety of topologies. Now, you'll notice that in many of the graphs that I describe, and many of the ones I will describe when we talk about these network experiments, I've played this game of doing random rewiring or adding random edges, which has the effect of reducing diameter. And one of the points I want to make in this research is that these abstract studies of topological properties of networks, like they have small diameter or they have hubs or connectors, are kind of meaningless if you don't talk about what's actually going on in the network. If you talk about the problem or problems being solved in the network, because the same kind of topological operation can have opposite effects on different problems. So for instance, if you do adding random edges or random rewiring in this sort of small worlds family, that helps coloring performance. Okay, so if you look at those cyclical structures where I was gradually adding more and more random edges, that actually helps the coloring performance in a statistically significant way. But if you looked at this clique chain family, where I started rather than with an underlying lattice, I started with this underlying chain of cliques, and I add random edges, that significantly harmed performance for the same problem. Okay. On the other hand, if you look at consensus performance in this same family of clique chains, adding those random edges significantly helped performance. So for instance, here's a little plot which might be hard to read, but what I'm showing you here is the average experimental duration, so smaller is better performance on this plot, as a function of this parameter p, which says how much rewiring I was doing in that pleat chain family. So down here, where p equals 0, you just have that chain of pleats. P equals 1 out here, you basically have a random graph. Here is the performance on the consensus experiments as a function of that value of p, and here's the performance on the coloring experiment. So it doesn't make sense to ask whether this random rewiring, this more global connectivity, is a helpful or harmful thing in the absence of talking about a specific problem. And again, if you look at the, it's definitely statistically significant, the difference, let's say, between the performance at small values of p and large values of p in both coloring and consensus. So this crossover is a real phenomenon. Okay. Other findings: preferential attachment is much harder than small world for coloring problems. So again, even from only local information, these preferential attachment graphs do seem to be more difficult for the population than even these small world networks where there's a fair amount of random rewiring. Now here's a very interesting finding. In the first set of coloring experiments, in a minority, but it's still a significant minority of the experiment, we actually tried, as an alternative to the local view, giving participants a global view of the entire network. Okay, so we would basically show them the entire network, every single color. Their vertex was clearly identified, their neighbors were clearly identified, but they could see the colors of the entire network. Okay, so a striking thing was that, okay, so the first perhaps not so surprising thing is that in this small worlds family, where we did show them a layout which had the cyclical structure around the outside, even if there were random chords in it, showing them this global view significantly reduced the solution time. Okay, so this doesn't surprise me so much, because once you realize there's this cyclical substrate and that you need to propagate, as I've showed you before, conflicts towards each other so they can be canceled, even though it's still a little bit surprising, even though people, remember, these people have never tried to two-color graphs in a collective setting before in their lives, and they're not allowed to talk to each other about what they're doing. So it's still not obvious that when you give them a global view, that they should immediately have the shared understanding implicitly of what needs to happen to solve the problem, but they seem to, in a sense that it greatly reduces the solution time. The more striking thing is that if you do the same thing for the preferential attachment graphs, not only does it not help, it makes it significantly worse to give them a global view. So here's the average solution time. We had, I won't go into detail, but we had 3 different information used. The low one, which is basically what I described, an intermediate version where they saw a slightly bigger view of the network, and then the high where they saw the entire network. This is the average solution time over many trials of the underlying cyclical family. So you can see that the low and medium only slightly help, but going to the high greatly helped. The striking thing about this plot, though, is what happened in the preferential attachment networks, where you can see giving them more information significantly harmed their performance. Having the global view badly hurt their performance. Okay, and you can conjecture many reasons about why this might be true that we can talk about offline. Okay, in general, the coloring problems seem to be solved much more rapidly than the consensus problems. So this is sort of a reversal of the categorization of these two problems from the viewpoint of centralized complexity. And so I make the only half facetious remark that it seems to be easier to get people to disagree with each other than to agree with each other despite NP completeness and the like. Okay, how much time do I have or not have? Okay, that's fine. So what I want to do now is describe to you these more recent experiments that we actually just finished writing the paper on in a networked trade model, and just some slight framing. In many ways, this is, a more narrow study than the ones I've described so far. But one of the things I like about these experiments very much, and that distinguishes from the earlier ones, is that, if you ask yourself the question, what does economics or any other field have to say about what a bunch of people trying to, three colorable graphs from distributed local information, what guidelines does any branch of science provide about what should happen? The answer is none. What's nice about these experiments, as you'll see, is they sit firmly within a microeconomic tradition of equilibrium theory. And so actually for every one of the experiments that we run here, there's a precise equilibrium prediction from economics or a sort of an extension of the economic models that we developed that I'll describe. And so what's very nice is, as you'll see in every one of these experiments, I can essentially go compute an equilibrium vector according to the economic theory, which would tell me exactly how much wealth each individual should have after the experiment and directly compare it to the behavior. And that's a nice thing about these experiments that the others don't really share. Okay, game overview. So the game overview, it's a simplified version of classic exchange economies if you're familiar with them, of the Arrow, DeBrew, Fisher variety, but as you'll see, we don't need nearly the richness of those models in these experiments. Players start divided into two equal populations of size 18 each, and so the graphs are all going to be bipartite. Okay, they're only going to be edges between the two sets of 18, not within the two sets of 18. Every player starts with 10 fully divisible units of one of two commodities. Let's call them milk or wheat, just for abstraction. I deliberately avoid the terms buyer and seller and cash because of the confusions or interpretations that they sometimes induce. So you're either a milk player and you start with 10 units of milk, or you're a wheat player and you start with 10 units of wheat, but you only value the other good. So how do I incent this? Basically, in this game, your payoff in an individual experiment is going to be proportional to how much of the other good you managed to trade for during the 2-minute experiment. And so in particular, your initial endowment of 10 units is worth $2. So if you trade your 10 units for 10 units of the other good, you get $2 for that experiment. If you got lucky and traded your 10 units for 15 units of the other good, you're going to make $3, so on and so forth. The exchange mechanism, so first of all, you can only trade with your network neighbors. So this is a model for exchange economies in which there are geographical, political, or regulatory, whatever constraints you want, that only let you trade with certain other parties, and those are your neighbors in the network across the way. You can only trade with your network neighbors. I'm not going to go into detail on it. It's in the paper if people want to see it. But basically, it's a simple limit order market. So, for instance, if you're a milk player, you can post to your neighbors across the way that you're willing to trade 2 units of milk for 3 units of wheat. And so when you do this, you're essentially specifying both a price, which is you want 3 for 2, but you're also specifying a volume, meaning that this trade might get executed, but not for the full amount that you requested, but at the ratio that you did request. Okay? So think if you're familiar with traditional US equities market, it's the same kind of thing. You can basically specify what exchange rate you're willing to trade at and what volume you're up to what volume you're willing to trade. Partial executions are possible. Note that this is a model in which the prices are on the vertices, not the edges, meaning which if you decide that you're willing to trade 2 units of your milk for 3 units of wheat, that offer is available for execution with any of your neighbors on the other side of the network. I can't say, you know, to this person I offer this exchange rate and to this individual I offer that exchange rate. So not to mention the nightmares of interface that would actually create. So you just, at any given moment, your action is simple. You just decide what offer of this form you're willing to make. You can update it, again, asynchronously anytime you want. And you're essentially just trading with the aggregated book of limit offers from your neighbors, right? So at any given moment, your neighbors have all made offers that are available to you as well. You make an offer. If at any moment your offer crosses in terms of the exchange rate with one of your neighbors, then an execution will result, maybe a partial execution. The trade takes place. There's no resale, so once I've traded some milk for wheat with Joe, those trades are booked, our endowments are reduced accordingly, and we continue to make offers to our neighbors for our remaining endowment. Okay? Is this clear enough? Okay.
What if there's like, do you go for the middle?
So it's just like equities markets. Good question, Joe. I can see you've been spending time on Wall Street. So it's basically exactly the same as in like the NASDAQ market, which is the priority for price is determined by the order on the book already. So if you put an order in at some rate of exchange and you're the arriving order, then you're guaranteed that you will execute at that rate or possibly better if somebody was already offering a better offer on the other side. Okay. Okay, so one of the nice things about this game is that it's relatively simple as far as exchange markets goes. And the only source of asymmetry by design is network position. Everybody starts with the same endowments. You're just either one abstract endowment type or the other. You know, the rules are the same for everybody. The only source of asymmetry in this model is what the network, where position is in the overall network structure. Okay. I'll go through this very quickly, but this is the kind of interface you have. There's sort of a vertical bar for each one of your neighbors in the network. There's a vertical line showing where their offer is. There's a horizontal line that means an execution takes place. So the way visually this plays out is, you know, you'll be changing your offer up or down, your neighbors will be changing your offer up and down. You know, in general, you might expect that you'll sort of creep towards each other and execution will take place and things continue. There's an action panel at the bottom where it shows you how much money you've made already, what your current offer is, and then there's a little form where you can change what your current offer is. Okay? And then again, you still have this information, which is important in this problem, about how many other neighbors each of your neighbors has. So in particular, if you understand this interface, which I think for the most part participants did, you know that this person has nobody to trade with but you. Okay? So if you think about that, and you think about this game, that should mean something, right? This person basically should be a victim of yours if you're smart. Okay? This person has at least one other choice, this person has two, so on and so forth. Okay, so I'm going to quickly tell you about, I think, the very nice, simple equilibrium theory that has been worked out for this model and how it relates to network structure. So first of all, again, this is, you know, an entire discipline unto itself, but let me quickly describe in English what I mean by an equilibrium in this model. An equilibrium is a set of prices or exchange rates for every individual in the graph at which the market clears, meaning that all of the goods, that the trades can be executed that will cause all of the goods on one side to go to the other side and vice versa. Everybody will spend all of their initial endowment. So there's sort of two conditions. The market should clear and everybody should only be trading with neighbors offering the best price. Okay, so it's basically a set of prices where if every individual is rational in the sense that they only will engage in trade with those neighbors in their neighborhood that are offering the best price in their neighborhood, that still everybody will be able to trade all their goods to the other side, and they will, by definition, be getting kind of an optimal bundle of goods and an optimal amount in return because they're only trading with neighbors that are offering them the best rate from their perspective. Okay, so it's well known, it's well known that in general, an equilibrium holds. You actually have to reprove it in the case of the network setting, because in the network setting, you violate certain technical assumptions that are made by Arrow and DeBrew in particular to prove their classic equilibrium theory. We can discuss this offline if you're interested in what those violations are. The interesting thing about the equilibrium theory is that it predicts that at equilibrium, different individuals will enjoy different wealth simply as a function of the network structure. Okay? So let me describe to you what that theory says. And this is work that I did with Sean Cockaday, Luis Ortiz, Robin Pimentel, and Sid Suri in sort of in a separate and much earlier piece of theory. So there will be no variation, let me start with the easiest case. There will be no variation at wealth at equilibrium if and only if the underlying network contains a perfect matching. Okay, so if there's a perfect matching subgraph, there will be no wealth at equilibrium. And intuitively, what should happen on that underlying perfect matching is that everybody should just trade with their partner in the perfect matching on a one-for-one basis, and everybody will basically trade 10 for 10. Okay? If there's not a perfect matching at equilibrium, the maximum or equivalently minimum wealth corresponds to a contraction property of the network. So what you do is you look for the subset of vertices on, say, one side of the network that maximizes the ratio of the size of that set to the size of their neighbor set. So intuitively, if you can find, say, a set of 10 milk players, and if you look at all of their neighbors, that 10 set of vertices only has 3 neighbors on the other side collectively. So you sort of have 10 being contracted down to 3. The 10 are in trouble, right? Because even if the 3 have other choices besides the 10, one choice intuitively that the 3 should have is to say, hey, you send us your 100 units and we'll send you our 30 units. And the 10 essentially don't have a choice. Now, you know, this isn't a proof of anything because, of course, in this game, the participants don't have the opportunity to do this kind of collusion, but this is how the theory works out, okay? And so one important thing to see is that it's quite often when people first see this model that they think that an individual's degree will determine their wealth. Okay, but you can see that this isn't really, degree might have something to do with, your degree isn't that important because if you're degree 2 and your 2 neighbors have nobody to trade with but you, that's very different than if you have degree 2 and each of your neighbors has 15 other people they could trade with. You'd much rather be in the first situation, okay? So there's a very nice theorem, and there's an algorithm which, as I mentioned, was discovered just a few years ago that can compute equilibrium in this model, okay? And so you can apply this to different types of networks, like preferential attachment networks, where you can prove, for instance, that in preferential attachment networks, the imbalance between the richest and the poorest will grow unboundedly with the size of the network, like a root of the size of the network. Whereas in random networks, you will essentially have no wealth variation. So just keep this theorem and theory in background as I sort of describe the results to you. So I'm again showing you samples from each of the different network families that we played with in an extensive experimental session on this game. We did one trial of just a simple actual perfect matching where everybody is not, there's no network per se, everybody's just paired with one other individual in the room. All the rest actually are connected networks. 2 cycles, just a simple cycle, and I'm just the color coding here is just distinguishing the 2 sides of the bipartite graph. A 4 cycle where we just added some more local edges here. You know, all of these obviously have perfect matching subgraphs. This is a hand-designed structure in which you essentially have 4 little sub-economies on the outside here, each of which is highly imbalanced. Sort of you have 6 of one type of player and only 2 of the other. And so if this was just an economy by itself, you'd have quite a bit of wealth variation. These 2 would be rich and these 6 would be poor. But we've added in these super traders in the middle who actually can trade with anyone that somewhat ameliorate these. These in general do not have perfect matchings, and so there's some amount of wealth imbalance according to the equilibrium theory. We played around with some Erdős-Rényi networks, which basically have no price variation, and also with preferential attachment trees, which have a high amount of price variation. I mean, you can see that if this person plays their cards right, they should be able to get all 60 units of endowment from these 6 down here. These more dense preferential attachment graphs, again, have no price variation. So I think of the 28 different network structures that we had, we did like 3 trials of each one of these topological families, and in general, I think about 11 of the 28 had significant price variation according to the equilibrium theory, and the remaining 17 did not. Okay, I'm going to just give you a few minutes quick summary of what happened in these experiments, some of which is quite interesting. So again, you have rather good collective performance. So this is what I'm showing you here, grouped by each one of these topological types and sorted by performance, is what fraction of the maximum possible payout the population actually achieved in an experiment. So you know, the maximum amount that, the max social welfare in any one of these experiments is $72. $2 times 36 participants. You can see in the pairs they almost got to 100%. And you can see it goes down from there. I'll say more about these cases where the performance seemed to be the worst. But if we just blur our eyes now across all the topologies, the overall mean is, you know, pushing 90%. So 90% efficiency of the market in economic terms. And furthermore, if you use the individual wealth levels, if I just sort of represent a network by the individual wealth levels as sort of sampled values and ask, well, does topology matter? And I look at a sort of, this is a correlation matrix in which for each pair of topologies, I'm showing you whether that family of topologies can be distinguished from one of the others by that signature of wealths. And black basically is significant distinction at the 5% level, and gray is at the 10% level. The upshot is that you can, you know, overall performance is strong, topology matters, and many but not all of these pairs are distinguished. And if you look at this diagram more carefully, you'd see that there are certain topologies like the pairs topology and the clan P0 topologies, which are sort of at opposite ends of this performance spectrum, which look different from almost all the other ones. Okay, and we'll say a little bit more about why that's the case in a minute. Okay, I think this might be one of the most interesting plots to come from these experiments, in which we're, again, what I'm going to show you a couple of slides in which I'm comparing in different ways the vector of 36 actually empirically realized wealths in an experiment by the population versus the vector of 36 predicted wealths according to the pure equilibrium theory. Okay? So what I'm showing you here on the left is a scatter plot in which there's a little circle for every experiment, for every network, and for every experiment. And what I'm plotting on the x-axis here is essentially a normalized measure of the standard deviation of the equilibrium wealths. Okay? So this axis is measuring, according to the equilibrium theory, how much inequality does there need to be in order to achieve equilibrium. So you can see there's a big pile of them that are down here at 0. These are all the networks with perfect matchings. Okay? And then it goes from there to, this is probably a preferential attachment tree where there's quite a bit of wealth variation. because you have things like that individual with 6 neighbors who have nobody to trade with but that person. Okay? So this is showing the standard deviation of the equilibrium vector, and this is actually showing you how much money people make, okay, the collective make, where again, the best you can do is 1.0, and that's the pairs, okay? So you can see that there's a very, very strong downward trend to this plot. The correlation between the correlation between the x and y coordinates of these points is a strong negative 0.8, and it's significant at well below the 1% level, okay? So this is basically saying that when the equilibrium theory predicts that you need to have imbalanced wealth in order to achieve equilibrium, the performance of the actual human subjects badly degrades the more that's true. Okay? So this echoes something I'll say more about in a second. This next plot is almost the same but different in an important way. The x-axis is the exact same thing. You have a big pile of things over at 0, which are the perfect matchings. It's simply measuring the standard deviation of the equilibrium vector. The y-axis is now measuring the standard deviation of the collective vector. So we have here sort of an interest, and by the way, the correlation here is a rather large 0.96, and again, it's highly statistically significant. In case you were wondering, for the statistical aficionados in the audience, these correlations remain similarly strong, even if you omit the pile of points on towards the left that have perfect matchings that you might think would dominate the correlation. Okay? It's not true, in fact. Okay, so this is a real phenomenon. And so you have this interesting two-part story. The greater the equilibrium variation, the worse the collective performance. But they're not totally ignoring it, because the greater the equilibrium variation, the greater the behavioral variation. So somehow people are, in fact, spreading the wealth more unevenly when equilibrium predicts that they should do so. But they're just leaving more money on the table. So you can almost think of it as like a two-part operation. The greater the equilibrium variation, the more money they just leave. But of the money that they do manage to distribute amongst themselves, it is in fact sort of closely modeling the amount of variation that equilibrium predicts it should. So this leads to this next plot, which maybe I'll skip from this to conclusions. Of course, as you can, you can imagine, there's endless analyses one can do on this data. So the last slide I really was showing you was about how well the equilibrium model does at measuring macroscopic aspects of the collective behavior. But of course, the equilibrium theory, it does a lot more than predict standard deviations of wealth, right? It goes around and for every individual in the population says, I think they should have gotten this much, they should have gotten this much, so on and so forth. And so you can actually do, instead of taking the two vectors, the behavioral vector of 36 wells and the equilibrium vector of 36 wells, and doing something crude as I did on the last slide, like computing standard deviations and comparing them, you can actually do a component by component comparison, okay? But then you of course have to have some measure of component by component comparison. So what I'm showing you on each one of these plots, for instance, is again a little point for every network, for every experiment that we did. And what I'm showing you here is I'm showing you a measure of how well the equilibrium theory, let's say in this upper left-hand plot, how well the equilibrium theory does at predicting the actual individual wealth in terms of L1 error. Okay, so I'm just basically going to take these two wealth vectors, the equilibrium and the empirical wealth vector. I'm going to normalize them so that they're actually sum to 1. So they're probability distributions now, they're wealth distributions. And I'm going to say, what's the L1 distance between the equilibrium prediction and the actual behavior, okay? And that's what the x-axis for each point is showing. The y-axis is showing you an alternate model, right? So of course I can go compute these L1 distances, but I have to know, are they better than some other explanation for the behavior? So the x values for each network here are showing you the L1 distance for that experiment between the equilibrium prediction and the actual behavior. And in this case, I'm showing you, in contrast, another reasonable theory, which is that we just predict that the degree distribution will determine the wealth distribution. The more trading partners you have, the proportionally more wealthy you should be, okay? So I can also compute the L1 distance between the degree distribution and the behavioral vector as well, okay? And so anything above the diagonal here is a win for the equilibrium prediction. So you can see that it's either a tie or better on every single one of 28 experiments. Of course, this is a highly significant result from the statistical standpoint. Another straw man or plausible alternative that we can compare equilibrium theory to is just the uniform distribution. Okay, so we just predict that no matter what the network structure is, whatever wealth gets distributed, however much or little that is, we just predict that it'll be uniformly distributed among all participants, 1/36 each. So you can again see that equilibrium theory is strongly beating that particular alternative explanation, okay, in all 28 cases. Now, one of the reasons that we decided to test against the uniform distribution was this earlier result in which we saw that the more inequality equilibrium prediction, the more money that gets left on the table. So one explanation for this is, and this connects with a large behavioral game theory literature on what's known as inequality aversion. So there are many, many experiments that behavioral economists have performed in which they've shown that a systematic way in which human subjects deviate from equilibrium theory is to basically move back towards more fair outcomes. Okay, so if you're familiar with things like the ultimatum game, where the equilibrium prediction is that one player should essentially walk away with almost all of the money, the actual splits that are observed in behavioral practice are much, much closer to 50-50. So this is why we compared it to equilibrium. And interestingly, the best model we found so far for the individual wealth behavior averaged across all 28 experiments is one in which you take a mixture of equilibrium and uniform. So you take the equilibrium vector and you take the uniform distribution. You have two probability distributions now, and you take a linear mixture of these two distributions. So if you do that and you look at the mixture coefficient, which is the weight on the uniform distribution, you find that there's a nice, very, very convex structure to that optimization, and that the best performance is achieved when you put about 75% of the weight on the equilibrium vector, but then you nudge it back towards equality by mixing in 25% of the uniform distribution. And that gives you this model here, which you can see is basically either tying the equilibrium theory almost always, but in a handful of cases it's improving it. This is not a statistically significant difference between the two models, though. Okay, I think I've said all this now. And then we have a bunch of analyses on the actual dynamics within a game, which are quite interesting, including on just how the bidding unfolds over time and how the prices fluctuate over time, and on a very interesting, the very interesting phenomenon of sort of liquidity or supply being fragmented by the trading that's taken place so far on the network, but I'll leave it to the paper to discuss that. Okay, quick conclusions. So, you know, maybe the most important one, which I didn't emphasize a lot, but which is, I think, obvious from what I've said all along, is that people can do this stuff. So people can solve a wide variety of relatively challenging optimization or collective problems on a wide variety of networks in short amounts of time from very, very local views of the state of play in the network. Structural, by which I mean kind of topological, network topological, and other effects can be both systematic and very, very strong, which is, of course, what made it possible for us to see these effects, even though I consider our sample sizes, both in terms of number of experiments and population size, to be relatively small. And this just summarizes some of the findings I've mentioned at one or, either quickly or in greater detail. Where we have an equilibrium theory, in particular in this last set of experiments, where we had a very detailed equilibrium theory directly relating network structure to predicted behavior, the behavior does seem very closely related to this theory, but imperfectly so. And of course, in the spirit of the whole purpose of behavioral economics in the first place, the point of behavioral economics is not to prove game theory wrong, but to prove game theory wrong, but show how it can be fixed, because in general, when there's deviation from equilibrium, it's not in some haphazard, arbitrary way, but with sort of consistent behavioral human biases that you might actually hope to model, which is what we're trying to do, for instance, when we take a mixture of an equilibrium vector and nudging it back towards equality. Okay? Future work, we definitely want to do more experiments. We're planning at some point to do an open source software release to anybody who wants to do similar experiments in their own institution. I mean, for this to really take off as a line of research, this is absolutely essential, because there's just no way one group can kind of cover the space of interesting experiments to do by themselves. I won't talk about it, but there's actually many, you know, wearing my other hat as a machine learning researcher, there's many challenges for sort of even modeling challenges for machine learning when you're talking about modeling collective behavior. In machine learning, we're generally, most of the time, talking about there's some fixed process in nature, and we want to closely model that process as well as we can, and we have very clear error measures. In a lot of the types of learning that are inspired by these experiments, you know, even if you posit that there are sort of parametric models for the behavior of each individual, and you might hope to learn those models from observed behavior of the kind of the type from the type of data that we gather from these experiments. Our main interest here is not in individual level modeling, but in sort of what those individual models say about certain properties of collective behavior, like will they be able to color this graph that we've never given them before, and so on and so forth. So let me stop there and take questions from anybody who has time. Yes.
There are two dimensions to each of these games. One of them is the network structure, and the other one is the regulatory structure in which the game is conducted. You vary the first one. I wonder what would happen if you vary the second one. Would your result stay the same? Would you change?
Well, so my usual answer to any question of the form, what would happen if you tried this thing that you didn't try, is I have no idea. So if there's one thing I've learned from these experiments, and just also, you know, it's very clear from the behavioral economics literature that small changes to anything, but especially to sort of the framing of the problem, can vastly change the results. So just to give an example of things that we've thought about doing, but you know, just haven't had time to do, it's a very natural question to ask if you just gave people, once you know, all these experimental sessions, we bring subjects in, we explain to them what they're going to be doing, we take them maybe through a sample or practice game so we make sure that they understand the game, the system, and the interface, and then we start playing, right? And all communication, you know, we proctor the experiments, we make sure that nobody's talking, communicating, except through the system. A very natural question to ask is like, well, what if we just said, now that you understand the problem, you have 5 minutes of open conversation with each other to coordinate in whatever way you want, but then once the experiments start, you know, nothing, okay? So it wouldn't surprise me at all if those vastly changed the results. And it wouldn't surprise me if it vastly changed the results either for the better or for the worse in terms of the actual human performance. But I completely agree with you, right? I mean, I mainly talked here, you know, we've kind of set up a framework in which we have certain knobs that we turn, network structure, the game being played, so on and so forth. But just the entire, you know, how you frame the experiments to people, whether you know, I mean, there's a huge literature on this, you know, the same game, and if you just somehow do something that makes people feel like they're part of a team first, like before they come in to do graph coloring, you know, you have them participate in some collective exercise that's completely unrelated to the experiments, but just gives them some sense that they're a team, these things can vastly influence the behavior. So these are great questions, but I would not hazard a guess as to what would happen if you did this kind of thing. Yeah, go ahead.
You mentioned that you were also interested in the heuristics that the people come up with and sort of analyze the behavior of the people individually. Yeah. But your talk... Yeah,
I didn't talk about that. In a longer version of the, well, not longer, but before we did all these other experiments, I used to talk more just about what happened in the coloring experiments. And the other thing we do in all these experiments, by the way, is we give people an exit survey in which we ask them to just describe what strategies they adopted, what strategies they thought other people were adopting. And so in the particular case of graph coloring, which is the main one that I've had the time to kind of go through those surveys and then also to check it back against the behavior, a number of interesting heuristics seem to be suggested. So maybe the most striking one was many people in one way of saying it or another essentially proposed things like the injection of thermal noise or randomization a la simulated annealing to just kind of shake up the global state or even the local state when they perceived that the population was at a stasis or a local minimum. So they would basically say things like, well, you know, if there was a color conflict in my neighborhood and all of the available colors were already used, I would just start randomly changing my color periodically in the hopes that this would shake things up. So there were many instances of people essentially, suggesting the use of randomization to escape local minima. Of course, they don't put it this way, but when you read it, as a computer scientist, you could clearly sort of take that away from it.
What class of people?
So in general, the demographics have differed slightly, but these are all, for the most part, Penn undergraduates with a little bit of background in networks, but not a technical audience for the most part. So I would say, roughly half of them might be scientists or engineering majors of one kind or another. Another half of them would be, from the Wharton School or just from, sociology or a liberal arts major. So, people getting a college education at a good place, but not with any special background on these topics. Another one on the coloring cases, people, very amusing one is people describing signaling strategies in coloring. And so one signaling strategy is, so one person described a signaling strategy quite sophisticated, where if they if there was more than one color that they could choose and still not have a conflict with their neighbors, they would kind of toggle between those two colors in an effort to signal to their neighbors that if it was useful for them to choose one or the other of those colors, they were just sort of expressing their flexibility to their neighbors. And so there were like 3 or 4 different signaling strategies. And then I would go back to the data and sort of look for actual instances of those signaling strategies. And you could see that, in fact, the people that said that they adopted those strategies did seem to have adopted those strategies. What I couldn't see any evidence for was that anybody ever correctly interpreted those signaling strategies in the way that they were intended. But so, again, this goes back to the earlier question, right? I mean, if you give people 5 minutes to talk, you could just sort of quickly settle on some signaling strategies.
Do one more question?
I have a question. What's the difference between behavioral economics and
I view what I'm doing as firmly in the tradition of behavioral economics. The only difference is, I think, first of all, I'm exploring a set of issues which I have not seen explored there yet, which is sort of a network structure issue, and also these issues trying to choose problems from computer science and related fields that we know something about computationally. And the next thing kind of goes hand in hand with the network part. But I think just the scale of these experiments is unprecedented in behavioral economics and game theory, where for the most part, you're bringing pairs of individuals in, many pairs, but you're bringing pairs of individuals in at a time to do things like play ultimatum game or prisoner's dilemma, so on and so forth. But other than that, many of the sources for inspiration and many of the specific methodologies that I've adopted here are directly borrowed from that tradition. And my view is that it would be a happy future if these kinds of experiments led to collaboration between computer scientists and behavioral economists on these sorts of experiments.
well, one element I'm seeing in what you, of course, you focused on the networks, but about the behavior, like you could be observing people. I'm not saying with cameras or whatever, but you could be observing their strategies, and maybe use them in your algorithms. Close to the way computer science would do, where let's say in the stock trade, right? How do they do?
Yeah, yeah.
There are strategies, right?
Right.
So how about the expert versus the novices versus all this?
Yeah. I mean, these are all great things, and I mean, it's interesting to also wonder about experiments in which you have a mixture of human players and automated strategies. I think all this is. Yeah.
Okay. Well, let's thank Michael again.
Thank you.